and the next domino following, so it's the first current that reaches threshold. I can touch it, it doesn't fall over. Push a little harder, it still doesn't fall over. Finally, it falls over. Okay, so my graded potential was strong enough to push that first domino over. The next domino falls over with a force strong enough to open the next set of voltage-gated channels, and it keeps going on down. That's what we'll talk about after break. Mechanically gated, you may open a few, you may open a lot, depending on the force that's being put on the cell. Ligand gated, you may have a few neurotransmitters, you may have a lot of neurotransmitters. And leaky channels, we see this changing most predominantly in heart muscle, all right, where we can, it gradually increases over time. Think of a leaky channel as a, like a hourglass timer, a sand hourglass timer, and the channel's open all the time, sand is constantly dripping or falling through that opening, and finally it reaches a level high enough to open a voltage-gated channel, okay? So the amount is going to be variable. All right, so the threshold potential, here's illustrating what I drew on the board. Let me write the words for those of you that are writing this down. This is a graded potential. You remember what that picture was illustrating. So on the board then, here is the synaptic gluton, one of which I've drawn here. Ligand-gated channels have opened. I suppose I could also label those. And a graded potential is spreading through the cell. Now in this case, it's strong enough to result in an action potential. But notice that it's, even though it's strong enough when it reached the axon hillock to trigger an action potential, it was still getting smaller and smaller. So it's moving, this is time, so it's going to be here, but it's less and less and less. It just happens to still be of sufficient strength to be of the voltage required by the action, the voltage-gated channels at the axon hillock. But it's still getting weaker and weaker. Okay?
So the potential, it will always, the location of the potential is significant at the hillock.
Well, the reason that this is significant at the axon hillock, we'll see when we get back from break, and that's because the voltage required is lower here than the voltage here. So these are,
Okay,
it's like that first domino. Yeah, it's like that first domino is thinner, but when it falls, it's a sufficient force to knock over each of the rest. It itself doesn't take as much force to push it over, but it's heavy enough that it will knock over the other dominoes, and each one will knock over the rest. So that first one will be easier to get to push over. Okay. So this is what we're reaching to. So here, obviously, these are not, a hyperpolarization is not going to reach threshold. Okay. This graded potential is subthreshold. Finally, this graded potential is threshold. Okay. So a threshold potential just means it is a current, a potential or a current which reaches the minimum required to open our voltage-gated channels. If it is a graded potential reaching threshold, we'll always see it as slight rise. So if it's that first push, knocking that first domino over, you'll see it as slight rise. If, however, it is one domino knocking over the next one, an action potential occurring along the axon itself, it'll just be a straight spike. So here's the current coming along, and it reaches a voltage-gated channel here. It's going to look like this. It'll be that graded potential, reaches threshold, opens an action potential, and we get a spike. Now, as that action potential goes down the channel and it opens the next voltage-gated channel, we already are going to have the current strong enough to open that, and so we're going to see just the spike. We're not going to see it as slight graded potential. Does that make sense? Because it's a huge current every time the voltage-gated channel's open. It's not just a slight current. So we'll always see just the straight spike, as if we had an electrode there and we just flooded it with immediately sufficient numbers of ions. All right, so let's stop there and take a break. Let's go till 10 after.